2004 Subaru WRX with a 2.0 liter turbo engine. Symptom is check engine light and a P0171 trouble code. Okay, quick shot of the trouble code. P0171 is our fault, and that's fuel system 2 lean. The first thing I think about when I see a lean condition is what is the engine operating parameters when this trouble code's set. So we're going to look at our freeze frame data next and see if this was an idle lean condition or an under load lean condition to give us some better direction. Okay, so here's our freeze frame data. This is fuel system 2 lean bank 1, our P0171 code. You see on this data capture, some of the main ones that I look for would be my engine RPM. You see we're at 2,900 RPM. Our vehicle speed, we're at 57 miles per hour. That's not as significant as our calculated engine load and the fact that our RPM is high, and both short-term, long-term fuel trim are adding fuel. As you can see, 22% on the short-term, 14.8 on the long-term. So what this tells me right away is this is not going to be a vacuum leak. I'm not worried about doing a smoke test on the intake. Of course, a vacuum leak is one of the many causes of a lean exhaust trouble code. This is an under load condition problem. So an under load lean condition problem. We're going to go after something other than a vacuum leak at this point. Okay, we have the engine running now. Next step in this process would be to look at some data on the computer. And mainly our focus with this lean exhaust trouble code is to see what our short-term and long-term fuel trim numbers look like. And you see my short-term right here is negative 0.7, basically 0, and my long-term is negative 10. So that's a little bit contradictory to what our trouble code showed us. What we can say from this right now for sure, no question about it, this is not a vacuum leak. A vacuum leak is not going to cause negative fuel trim numbers, which is taking fuel away. So what we're seeing right now with the engine idling is this engine is actually running a little bit rich based on this negative 10 long-term fuel trim number. Now it has been corrected for. Short-term looks good. You know, I don't need to graph the O2 and look at that right now. That's not the point. What we want to do is raise the RPM and take a look at this long-term number and short-term with a higher RPM. We had a little bit of counter fuel trim on the short term going negative while the long term was positive, but you saw at least at one point in time around 3,000 RPM we were about 15% on the positive side of these fuel trim numbers, long term at least. So what that's showing me really is two things. One, at idle we're running rich, and then two, under load conditions, higher RPM, not really a load here, we're in the shop in neutral dead rev, but under higher RPM conditions, higher airflow, we're actually running lean. And the first thing that we think about when we see something like that is a dirty mass airflow sensor. The theory behind that is a little bit goofy. We'll talk about that in a minute, but our next steps that I want you guys to look at would be, we're going to do some before and after stuff here. So we want to focus on we're idling right now and what our mass airflow grams per second reading is. We're reading 3.29 grams per second. So just want to throw that number out there, see where we're at later. Long term, still negative 10, short term at 0. It's pretty balanced out. Remember that number, 3.2 grams per second on the mass airflow. Unfortunately, they don't give us mass airflow voltage on this scan data, so we'll do some checks manually at the sensor next. Okay, this is a 5-pin mass airflow sensor. When you see 5-wire mass airflows, generally speaking, the intake air temp sensor is part of the mass airflow. And so that makes for easy troubleshooting when you understand that a mass airflow needs a power, 12-volt feed, a ground, and then a signal, and then the other 2 wires, 5-volt reference or signal for the thermistor, and then a ground for that. Very easy to go through this and figure out which one our signal wire is. We're just going to go through each wire and figure out which one moves with throttle angle changes, with airflow changes, When we find that wire, that's going to be our signal wire, and that's the one we want to focus on. All right, so we're connected to the middle wire on this mass airflow sensor. That is my signal. I'm going to get you focused on the screen here in a second, but what I want to show you guys is a way to make the signal cleaner. And what I'm going to do, I have an extra T-pin right here. This is the sensor ground. I'm going to connect my black negative lead off of the battery and connect it to the sensor ground wire and show you the difference on the scope itself. Okay, so some preliminary numbers. We're looking at 1.37, 1.35 volts on the mass airflow signal. If I rev it, you see it reacts with airflow changes. If you guys don't like the hash that's in the signal, you can always use the sensor ground. So instead of the battery ground, I'm going to go to the sensor ground now and show you the difference in the signal. And that's a real good lesson on why sensor grounds go to the computer. That's what the computer sees. It compares the ground circuit that has noise on it to the signal circuit that has noise on it, and it reads difference in potential, cancels out that noise. That's why sensor grounds go back to the computer. So a lot cleaner signal. If you guys like that better, you can adopt that in your testing methods. So again, looking at a little bit cleaner signal here too. 1.2, 1.3 volts is live. Do some snap throttle tests. You can hear right away there's a hesitation to this. I'm going to do a real quick snap. Looks like we hit 2.9 volts on a peak. Normally what you would have is a real quick inrush of air, and you get an initial spike on a mass airflow signal that I'm just not seeing. And normally that's achieved by letting the idle all the way back down and very rapid snap. There should be a spike right here at the beginning. I'm not seeing that. This is suggesting, again, a dirty mass airflow. 3.1 volts was my peak on that snap right there. 3.126, and what I generally look for is over 4 volts. On an analog type mass airflow sensor like this one, I'm looking for over 4 volts. So it looks like it's dirty. That would definitely give us our positive fuel trim numbers under a load condition. To explain the rich condition at idle speeds, I want to give props to my friends over at IATN, because this is where I read this. It was one of the guys over there talking on one of the forums had mentioned the characteristic of how does a dirty mass airflow overestimate airflow at idle speed. And I don't remember his name. This is years ago that I read this, but I'm going to adopt it because it makes sense to me, and it's really the only explanation I can think of that fits. And to answer it, it would be that the surface area of that hot wire has actually increased with the carbon deposits on it. In environments of low airflow with a bigger surface area, it actually dissipates heat more than what it should be. And so by it dissipating heat with less airflow, it overestimates airflow. I'm going to go with that explanation. It's the only one that I can see matches where you can have a contaminant that is shielding or keeping the hot wire hot, which is the theory behind it. But at low airflow, closed throttle positions with very small amounts of airflow past the mass airflow, it actually cools the resistor more because of an increase in surface area. So that's what we're going with. Let's pull this mass airflow apart, see what it looks like, and then we'll look at the results after. Again, remember our grams per second reading on the scan tool? We were reading roughly 1.2 to 1.3 volts right here at idle. I expect that number to come down after we clean it, and I expect this number to come up after we clean it. All right, we got the mass airflow removed from the car. Our main thing with removing it was to make sure that it was a hot wire type mass airflow and that it was cleanable. Some of these are not cleanable, so I want to be clear on that. You can't clean every mass airflow sensor. So looking at the sensor removed, I've seen some really horrible information on YouTube before. So you guys got to question everything you see for sure. And there was a video where there was a guy actually cleaning this part right here. This is exactly like the Toyota dirty mass airflow case study video that I shot. It is the exact same mass airflow sensor. This is your intake air temp sensor. This has nothing to do with how the mass airflow signal reads. This is a separate sensor. It's just housed in the same place. So don't touch that. Cleaning that will do nothing. Your resistors are inside of here. See if I get the right camera angle and lighting here. Wow, this is a pretty tough shot. Try to get as close as I can and show you guys the contaminants that are on these hot wires. This is a hot wire type mass airflow. When you see this style of mass airflow sensor, it is cleanable. And hopefully this is showing up on the camera, the contaminants that are on this. We're going to clean it. A lot of debate on what you use to clean it. I would not argue with those that want to use the specific mass airflow cleaner, and that's fine. I've been cleaning these for 20 years with brake clean, carb clean, the non-residue kind, the stuff that does not leave a residue on it, and I've had zero issues in doing that. Some of you want to take argument with me on that. That's fine. Use the CFC mass airflow cleaner by all means. I'm not going to argue that. Something else that I do is spraying this is not going to be enough. I need to get down in there with a very soft brush, and I need to dust those contaminants off while I'm using the cleaner, because I've seen the cleaner just not take it all off. So I'm going to do that. I'm not going to be able to show it to you on camera because of, you know, I can't even get you the shot of the resistors, let alone showing you cleaning it, but I'll show you the after when we're done. Okay, real quick back to this. Just want to identify again which ones are cleanable and which ones aren't. You see there's two resistors in this one, and there are some out there that have single resistors. They look just like this. And so I want to be clear that the only ones that I've had success cleaning are this style. If they don't look like this, then I'm suggesting not to clean it. So GM, Ford, Toyota, Nissan, Subaru, some, and I want to say some, not all make Subarus, not all make GMs can you clean. I think the newer ones, they redesigned it. So again, if it looks like this, you're safe to clean it. Be careful. We need to get the contaminants off these resistors as best you can. Okay, here's the after shot after cleaning it. Hopefully that's showing up pretty well. Those are very clean now. Of course, cleaning a mass airflow, you never want to do it with it plugged in or with the key on. And we don't want this hot wire to be hot when you're doing it. You'll ruin it. And you know, there's a lot of debate about cleaning mass airflow sensors in the field. Guys, I've been doing it for 20 years and I have not had one single comeback that after I cleaned the mass airflow, it somehow damaged it or caused some type of condition where the car wasn't quite right and it had to come back and get a new one. So, you know, to each his own, I guess. You want to replace it, replace it. I've had a lot of luck cleaning them. Let's see what our after numbers look like now. All right, before we do these after pictures, I just want to talk about this again real quick. That what we were saying, what we were trying to plug in our numbers was that this one is our idle speed and that we expect that to now read lower than what it was before. But more importantly, for our lean condition, what we expect to see is some big spikes on initial snap here, and I want to see voltage that goes over 4 volts on a wide open throttle snap. So I'm not overly concerned if our idle voltage numbers don't change much, and that there is a realistic possibility that there's something else causing this engine to run a little bit rich at idle speeds, and that we didn't correct that problem. But what we do want to see is a big time correction under load condition, higher RPM conditions. That's our main complaint, lean exhaust trouble code. That's what we're trying to fix. Hopefully this is all encompassing, that we fixed all of it at once. Let's see what happens. I'm reconnected to the mass airflow. I'm going to start the car back up. Go ahead and unfreeze that picture. All right, so we got the car running. We're at idle, connected like we were before. I'm reading 1.19, 1.17, so it is a little bit lower than it was before. And you know what? We're going to miss our window of opportunity. I'll come back to this. We'll do our snaps here in a second. Let me go back to the scanner, and I want to look at our fuel trim. What's happening now is we probably have a correction that has already occurred. We've been running this long enough that maybe we should have focused on that first. You guys remember what our grams per second was before? I think it was like 3.2 or something like that. And we're now reading 2.88. You see my long term is now negative 4.6, and we were at negative 10. And you look at the short term and it's adding fuel. So we're still catching the tail end of this correction taking place, that we did in fact fix this rich condition at idle from cleaning this mass airflow. So let's watch this for another minute or so. See, short term is adding fuel and long term is taking it away. Those are countering each other. I've covered this in some of my other videos. This dirty mass airflow on this vehicle did cause a rich condition at idle speeds. I have to tell you guys, most of the time you don't see this. A lot of people think you see this every time you see a dirty mass airflow. That is not the case. Most of the time you won't see a negative at idle. It'll just be normal at idle and be positive at higher loads, higher RPMs. In this case, you saw both. That was the main reason I wanted to film this one, is to show that. We still have a short term of a little positive, but we're within reason now. We're at 7.8. We'll see this long term correct. That's going to come up. We're definitely within that plus or minus 10%, but we are no longer rich at idle. Again, 2.6, 2.5, same idle, same RPM, same airflow. So what changed? What changed is the way the mass airflow was reading the airflow. We now have less airflow indicated by the mass airflow, even though there wasn't, but less airflow indicated means less fuel commanded, means this vehicle is not running rich anymore at idle speed. Let's go back to the scope now and see what our snap throttle numbers look like. Okay, so back to the scope. I'm just using a graphing multimeter mode here. You see we're 1.17, 1.18. Not a whole lot different from before, but that was enough of a difference in airflow to give us a rich condition. We'll do some snap throttle test now. See that initial first spike we were not seeing before? Still only hit 3.2 on the peak of that, but that initial spike was great. Now this mass airflow sensor may be calibrated a little bit differently with the turbo, that it needs to spool up before you see higher mass airflow numbers. So I'm not going to worry too much that I'm not seeing 4 volts on this one, even though that's the baseline number I want to see typically. Watch that first spike. You can actually hear how much faster this engine revs too. You can hear it, you can see it. So I'm only hitting 3.3 on the spike, but again, I'm not worried about that. This is a turbo engine. I'm not letting that turbo spool up. When that turbo spools up, we're gonna get a lot more airflow. And we need room to be able to read that. So I think that can justify that. But that initial first spike, it looks great. We were not seeing that before, were we? Not that kind of reaction at all. All right, last thing, we're gonna go back to the scan data. And what we want to look at is our higher RPM fuel trim numbers. Remember, we were very positive before. What I expect to see, looking at these two, short term, long term, what I expect to see is my short term go very negative and my long term still being positive because the memory is still there of a lean condition. So let's watch it and we'll be able to tell if we fix this vehicle. That's your memory. There's the counter right there. Pause that. Hard to talk over that. Just want you to, this is paused right now. I want you guys to focus on the short term and long term. And this is what I was talking about with a couple other case studies, is when you see short term counter the long term at that given load and RPM combination, you fix this car. We fixed this lean condition. I have no doubt in my mind that this vehicle will leave and will not come back with a lean exhaust trouble code. That is a fix. All right, one last comment on this. Wouldn't be a bad idea at this point, disconnect the battery, wipe out all that memory, or we can just drive it too. It will relearn itself. This vehicle is a fix. I think the only thing that I don't like about the final test results is seeing only 3.3 volts on the mass airflow signal at wide open throttle. But again, this is turbocharged, and I believe with that turbo being active, we'll see a lot higher airflow and that number would come up. So on a test drive really would be involved to see that number go over 4. I believe it will over a test drive. And the debate for sure is still there on whether or not you want to replace the mass airflow or clean the mass airflow. I'm saying this vehicle is fixed with cleaning it. So I hope you guys like that. I think the most important part with this, not the mass airflow replace it or clean it debate, but seeing a mass airflow overestimate airflow at idle speed and underestimate airflow at higher RPMs. That's the main point of this, and you saw it with this video. Hope you guys like that. Okay, I lied. We're not done. Just wanted to get a final shot. This was on a test drive. Wanted you guys to have some numbers. And you see at our peak, which is roughly in this area, that I'm reading 4.099 of a volt. That's what I wanted to see on an analog type mass airflow, hot wire mass airflow over 4 volts. We are seeing that. And we got a grams per second reading of 183.15. This is where we wound out first gear, and then we had a shift into second. And so just some numbers for you guys for maybe comparisons. And that's it. Over 4 volts on a mass airflow. That's what we want to see. Dirty mass airflow on a Subaru.